I'm very happy to be here among the students. So I will just start my lecture for today. So as you all know, I will be discussing the event generators, and also we have to, I think, judge the students. So I first request that maybe I should know how many students in this audience are between 1 to 2 years. Can you please just raise your hands in the chat box so that I can understand. Between 1 to 2 years. Okay, I see 5 students. Okay, I think not many. Is it true, or people are not?
%20%, Lokesh.
Okay. Yeah, I see few more hands now. So that is good. And now I am going to just ask one more question that please lower your hands just to understand how to begin with. And how many of you know the event generators, like how many of you are running event generators like PYTHIA and AMPT, just to understand so that we can plan the lectures accordingly. Okay, I see few hands, but not many. Thank you for this input. It will be important to carry on the lectures. So let me start now. Let me share the screen. And so can you just tell me if you can see the screen?
Yes, sir, it is visible.
Yes, sir.
Okay. So as you know, I will be starting the event generators, and just a minute. Yeah. So what I'm going to cover in these 3 days, I am listing here. On day 1, we will be just giving some introduction, basic principles, and brief details of Monte Carlo event generators. And on day 2, we will be giving introduction, brief details of PYTHIA model, and we will also do hands-on experience on it. And on day 3, we will study the AMPT model and also hands-on experience on this. So after we finish, I hope you will be able to understand what are the event generators and what are their basic principles. And I hope you will be also able to run PYTHIA model as well as the AMPT model. So with this, I think we can begin. So I will start with a typical high energy event, for example, a PP collision and a possible processes as shown in this schematic diagram. And there are various processes involved in this event, which are shown here in different colors. So what are those processes? This you can see here, it is a hard processes, and it represents the high momentum transfer process. Then you have the parton showers, that is shown by this green color. The scattered color charges emit gluons. Then you have underlying events, which are shown here. These are the secondary interactions among the parton remnants. Then you have the hadronization, in which the partons get confined into the hadrons. And finally, you have, if any, unstable particle that will decay further. So as you can see, this is a very complex structure. So to quantify these collisions, we actually need accurate simulations. And in addition, in order to verify a potential discovery from experiments, we also need some accurate simulations. For example, a majority of recent Higgs discovery plots rely strongly on the Monte Carlo predictions. So that is the importance of the event generator or these simulations. So with that, I will mention you what are the event generators. So basically, event generators are the computer programs which generate physics events in very layman language and as realistic as could be using a wide range of physics processes. For example, you could generate events for PP, PA, and AA collisions. These event generators basically use Monte Carlo techniques to select relevant variables according to the desired probability distributions and to ensure randomness in final events, making them comparable to real experiments so that you can compare with the real experiments. Then these event generators also give access to various physics observables. You could do all different sorts of analysis as you will do in your data analysis. And these models, these event generators are different from the theoretical calculations, which mostly are restricted to one physics observable, for example, kind of freeze out type models. And finally, the output of event generators could be used to check the behavior of detectors, how particles traverse the detector, and what physics processes they undergo. All these things can be simulated in programs such as GEANT. And you know that many of you might know that you could estimate efficiency and acceptance of detectors using this. So for completeness, let me go through various applications of event generators, which we might be doing. For example, you can interpret the observed phenomena in data in terms of more fundamental underlying theory. And you could also give a physics prediction for experimental data analysis using the event generators. You can also generate distributions that look sufficiently close to data so that you can have the detector calibration, and also this help to plan a new detector, which you might think. Then as I mentioned in my last slide, you must be, many of you might be doing this, estimate detector acceptance efficiency corrections to apply on raw data to extract the true physics signals. And then another application is that you can devise analysis strategies which can be used on real data. For example, you can have some estimation on signal to background conditions for some rare signals. So these are the various applications. And then it will be interesting to also know how the event generators differ from the real experiment. So in real experiment, the collisions happen inside the machine, right? And then from there, you have events and tracks. Those are detected by the detectors, and the data are written on tape through data acquisition system. And then you can reconstruct those events and tracks, that is electric signals are translated into tracks, energy deposition, inferring momentum and particle species information, and so on. And finally, you will do a physics analysis. So this is the data analysis process which you go through. And then event generator are basically based on some known physics processes. You generate events, and from there you do the physics analysis. Either you make comparison to the existing data, or you can make predictions for the any future observable or data. And also we mentioned that you can send this output through some detector configuration event reconstruction chain, and you can help that to get some efficiency corrections and so on. And in real experiment, as you can understand from this process, that the information is only available at the final stage, that is at the reconstruction level. However, for event generators, you know the information at both initial or generation level and final or reconstruction level. So we can say that event generators are very powerful tool for a detailed, realistic understanding of physics, what we are doing. Then I would just mention you what are the challenges in simulating high energy events. So in addition to simple elastic collisions, we need to modulate a multitude of effects. What are those effects? For example, the particles radiate, gluons radiate off the quarks. Then incoming particles, those are confined in the bound state, for example, quarks and gluons in protons. Higher order corrections in perturbation theory are too laborious to compute beyond first few orders. Those are hard to implement. Then phase space of the final state particles is huge and variable in number of dimensions. For example, at LSC, the produced particles are of the order of 1,000 and the phase space integrals can be 3,000. And finally, many effects that cannot be described by the perturbation theory, but they need to be modeled. So how to handle these kinds of challenges? One of the options is due to the large dimensionality of phase space, computer simulations using Monte Carlo techniques can be used. So what are the Monte Carlo techniques? Monte Carlo techniques are the numerical techniques for calculating probabilities and related quantities by using sequences of random numbers. So what are the typical steps for a single random variable? Those are listed here. A series of random values, for example, R1, R2 is generated according to a uniform distribution in the range 0 to 1. And then this PDF looks like something like this. This sequence R1, R2 is used to determine another sequence X1, X2, such that X values are distributed according to a PDF fx of interest. And these X values can be treated as simulated measurements. From these simulated measurements, probabilities of X in a certain region can be estimated. For example, probability of X in A to B region can be given by the integral of this quantity. Okay, so what effectively Monte Carlo technique does is effectively one computes the integral of fx. So this is the very effective method, especially in multi-dimensional problems where a joint PDF fx, y, z, so on over a complicated region may not be feasible by other methods. So I will discuss a little bit about it in my later slides. So now I'm going to tell you about the Monte Carlo integration. So basis of Monte Carlo methods is on the fact that value of an integral can be written as the average of an integrand. So as you can see from this equation, this integral of fx dx can be converted into the average of fx. For n values of x, which are uniformly distributed in x1, x2, one can write this average of fx in terms of this quantity and your integral becomes this. And one can draw the xi values randomly using a uniform random number rho I as given by this equation. So basically you are calculating the integral as a function of average of a quantity. So what is the accuracy of this method? So this is employed using the central limit theorem. And as per this, the distribution of average x tends to Gaussian with standard deviation sigma MC is equal to sigma by root n. where sigma represents the standard deviation of fxi. And as you can see here, the inaccuracy or error simply decreases as 1 by root n. Usually in the generators, one defines the weight Wi given as x2 minus x1 times fxi. Then the integral becomes simply the average of weight I, which can be written as in, is average of weights. And one can define variance like this quantity, and you can get the this standard deviation by sigma by root n, because Vn is sigma square. So you can write sigma by root n as Vn by n under root. So finally, the value of integral can be then given by this integral value and plus minus this accuracy or inaccuracy. So how to improve the accuracy of this measurement? Either you want to increase n, right? Or you could decrease this numerator Vn. So there are some methods available by which you can do this. So how this accuracy or convergence compare of Monte Carlo technique with other common techniques which you can be using for numerical integration? For example, as we discussed, the error using MC technique is of the order of 1 by root n. And if you compare it with some other method, that is, let us say, trapezium rule, it is 1 by n square. And similarly, for Simpson rule, it is 1 by n4. So as long as your dimensions are less, so these two methods give you the good results. But when you go to the higher dimension, let us say some d dimension, so MC integration by always extend trivially and converges to 1 by root n. However, for trapezium rule, we get 1 by n raised to power 2 by d, and it becomes worse than Monte Carlo for d greater than 4. Similarly, for Simpson's rule, we have 1 by n raised to power 4 by d, and this becomes worse than MC for d or dimensions greater than 8. So thus for LSC events, where, as I mentioned, is of the order of 1,000 particles and so many integrals, the Monte Carlo integration is only a viable option. So that is why you would use Monte Carlo integration in these kinds of events generators. So what are the typical steps of those integration and full event generation? I list here. Basically there are two steps. In first step, you do the Monte Carlo integration and scanning. What you do is you take endpoints randomly according to some distribution. Then you accumulate the weights, as I mentioned in our previous slides. The cross sections and corresponding error are computed as given by the previous equations. Then you have at the same time, you have the phase space point which have the maximum weight W max is stored. And in step 2, we generate unweighted events using hit or miss method. What you do is you go through the randomly chosen endpoints and obtain the probabilities of those points, Wi by W max. You generate a random number between 0 to 1 and compare this probability with that random number. If it is greater than R, you accept the event, otherwise you reject it. And you repeat this process until the desired number of events and event are collected. So now we move towards the structure of a generic event generator. And in my first slide, I showed you a diagram where there was a typical PP collision and there were a lot of processes, and how you implement those processes is what is needed. So as I mentioned, high energy events are very complex, giving thousands of final states particles at head-on colliders. And luckily, these probabilities of separate stages of the events, they factorize in some approximations, And then you can have those approximations stepwise used to get the full event simulation. So let us see those steps. So first one is the hard process generation, as you can see. So these are generated by choosing a point on the phase space according to hit or miss method. Then you have a heavy resonance decay. Basically, those resonances have very narrow width and are decayed as soon as they are produced. And then you have the parton showers, as you can see here. So incoming partons are showered, as you can see here. These are called the initial state radiation, and any particle, any color charge particle in the final state is also radiating, which is called the final state radiation. And then you have the multi-parton interactions, as you can see from here. So these are the secondary low energy interactions between the partons within the colliding hadrons, modeled as QCD 2-to-2 interactions. And finally, you have the hadronization. What happens is the clusters of colored particles are formed, as you can see here, and hadrons are produced. And some kind of cluster model of hadronization is used. Unstable hadrons are subsequently decayed, as you can see here. So this is how in event generators, various steps are involved, and the full event is generated. So this is interesting to see. With that, I move to categorize the high energy event generators. Basically, based on their application, the event generators are broadly categorized into two areas. One is the particle physics or elementary collisions, we can call, and another is the heavy ion physics, where heavy nuclei collisions are taking place. And basically, the heavy ion collisions are representing many elementary collisions, right? It is just like many PP collisions. Almost all event generators for heavy ions contains parts which get borrowed from the event generator. So whatever the starting points of the elementary collisions event generators would be used, can be used for the heavy ion collisions, and then you can build it from there. So there are some key differences between them in terms of implementation of various processes. So those are listed here. And first one is the medium formation. Basically, in PP type collision, you will not expect a medium formation. In heavy ion collisions, a dense medium formation is expected. Then you have a hadronization environment. It is very simple in particle physics, PP collisions. However, it is complicated in heavy ion collisions. What about hadronic final state interactions? It is almost negligible in PP type collisions, but they are very important in heavy ion collisions because of this dense medium formation. And then background processes, this can be simply defined in a PP environment, but not easily defined in heavy ion physics. So few things you must note that recent results on multiplicity detectors, multiplicity dependence of PP collisions at LSE, they also show some effect which you would associate with the heavy ion collisions. So in principle, it would be good to have event generator or model which you could use in both PP and heavy ion collisions. So there are some event generators which can be used for both type of collisions, for example, PYTHIA and HIJING. So then I just list here some commonly used event generators, basically those which are used in STAR and ALICE. So first one is PYTHIA, then you have FOJET, then you have Herwig for PP type collisions, basically. Dominantly, these are used. Then you have for heavy ion collisions, HIJING, AMPT, and UrQMD model. Obviously, there exist many more, so you will definitely try to look at them and see where they can be used. So now I'm going to tell you few recent results and in which these model comparisons are done. First one is for PP type collisions. These are the star results where average charge multiplicity densities for towards, away, and transverse regions as a function of leading jet PT are plotted. And these are compared with the models which are shown here, PYTHIA 6 star, PYTHIA 6 and PYTHIA 8 with some tuning. And you can see that the models qualitatively describe the data. Then on the right hand side, we see the results from Alice experiment, where you plot the ratios of PT spectra from model to that measured in the Alice experiment, and x-axis is PT. Various particles are shown: pion, kaon, k short, phi, proton, lambda, xi, and omega. And qualitatively, you can see various models, those are compared, like PYTHIA 8, PYTHIA 6, EPOS LSC. Those show some qualitative behavior, but not explaining the data fully. So that is also interesting to note. Then for heavy ion collisions, as you can see from these plots, this represents the goal 200 GeV, and this represents 5.02 TeV P-lead collision. What is plotted here is the spectra at mid rapidity for pion, kaon, proton, lambda, xi, omega, and these results are compared with the AMPT model calculations. So you can see that qualitatively these models try to explain the data. And on the right hand side, what is shown is the yield difference in the near side and away side versus PT associated. The yield difference is between out plane and in plane, mid plane and in plane. And these are the results from data, lead collisions at 2.76 TeV. And data shows such kind of behavior, and it is compared with the Jewel model comparison. And you can see model try to mimic the data here. So what we learned from these measurements is that most event generators qualitatively describe the experimental data. However, it is difficult to construct an event generator which can consistently fully describe the experimental data in terms of various observables, energy, multiplicity regions, collision systems, and kinematic ranges. The event generators are also tuned to include the relevant physics processes by looking at the behavior of experimental data. Nevertheless, the event generators are very necessary and important tool to improve the physics understanding of the behavior observed in data. So with that, I am going to give you some exercise and homework for today, if you understood today's lecture. So I am going to give you the basic Monte Carlo problem. That is, you need to calculate the value of pi using hit and miss method. And hint is given here. You can calculate it by dividing circle area of radius 1 unit to the circle area of side 1 unit. You can generate random numbers, x between 0 to 1, y between 0 to 1, and try to get this value. And in B part, you show the results for different iterations and note your observation. And finally, if you are conversant with the root, you can plot the first quadrant of a circle superimposed on the square, just like shown here. And on the second part, I would like to ask you to go through the list of various event generators which can be used for PP and AA collisions in star and Alice. Give their underlying physics just in a couple of 2-3 lines if you understand, and differences among each other. and also tell which of them can be used for PA type collisions. So with that, I'm going to finish this lecture, and please have fun doing this. Thank you. And any questions or comments we can discuss.
Lokesh, may I ask?
Can you, okay, yeah.
Yeah, can you go to your slide number 20?
Just a minute, I will.
I do not know if you are you have come across to that point or not, because I was trying to see that in PYTHIA, but I did not get any, at least any information, at least on written in PYTHIA. So in your slide 20, you showed some of the event generators. PYTHIA,
Yeah,
HIJING,
I think you
AMPT,
can see,
Herwig.
right?
No, your sharing is off, I think.
Is it? Okay.
Looks like, yeah.
Just let me see. Can you see
Yes.
it now?
Yes,
Okay.
yes. So,
Okay.
so my question is, do you come across about the working range in terms of routes for these models? For example, PYTHIA, let's say, suppose one want to run PYTHIA at very low routes. So is there any working range for these models?
Yes, I was actually going to cover PYTHIA and AMPT in my next lectures, and there I was going to mention the range. I think there is
in terms of routes.
There is some low range for PYTHIA, I think. For AMPT, basically you can go from lower energy also.
So
but for PYTHIA, I think there is some constant. Yeah.
Okay. AMPT can be used for this CBM energy, at CBM energy, right?
You mean at what energy?
Let's say 6-7 routes GeV.
Yes. We have used actually around 7 GeV. Yeah.
Okay, thank you.
Hello.
Then there is a hand raise.
Yeah, I am not able to see the screen.
Yeah, I can see Rakesh. I will just moderate. So
maybe I will
Rakesh
go
Nayak. Yeah, Rakesh, just you can switch on your mic, your video.
Yes,
Also.
sir. Am I audible, sir?
Yes, to me.
Yes.
Yes. So, sir, I was generating some events in PTI for EP collision, and I was trying to like vary the virtuality Q square from 1 to 10. But when I was switching the channel like PDF lepton to gamma on, then I was getting no entry when I'm putting like Q square cut from 1 to 10. So I have that doubt like why I'm not getting that entry. So maybe I can mail you my problem in details and
Yes, and
we can
also
solve.
I think Rakesh is.
Yes, sir.
Yeah. So we will also go through PYTHIA tomorrow, and
Yes,
you
sir.
can mail me after this class, and we can also discuss there.
Yes, sir. Thank you, sir.
But just one thing, Rakesh, since you were
Yes, sir.
telling about the Q square, right?
Yeah, yeah.
Momentum transfer. So I think there is some lower cutoff there. Even for this proton case. 1
Sir,
GeV, I think is above certain. I think 3 or 4 GeV, 3 GeV, if I remember correctly.
Actually, I was doing the same simulation in PYTHIA 6, but there I have no problems. But in PYTHIA 8, I was getting no entry when I was.
Have you checked the cross section with your Q hat value?
No, sir. I was.
Just because when you run PYTHIA, then it writes the cross section, right?
Yes, sir.
Prints the cross section. So you don't have to run for so many events. You just run it for few events. It will write the cross section, and then with Q you write the Q hat. You not the Q square. You write the cross section, and probably you will see that below 3 GeV the cross section remain constant. If I remember correctly. So that you can check quickly.
Actually, when I was generating like for q square in the range of 0.001 to 0.01, like so very small, then I was getting everything like all right. But when I was trying to vary that for higher q square, then I was facing some problem.
That could be something else, but what I was telling is little bit different. So maybe
Yes, sir. I will try that. Okay.
Anyway, Rakesh,
Thank
you
you.
can send an email and then we can try to look at that tomorrow also.
Yes. Yes, sir. Okay, sir. Thank you, sir.
Lokesh, I have another request. I do not know. So tomorrow your plan is to teach?
Yes, yes.
No. What is the kind of, you showed in the beginning some plan for
Yeah.
tomorrow?
Let me go to that slide.
Mhm.
So basically, I will be going through PYTHIA model, its introduction, and I will show them how to run the PYTHIA and maybe give them some hands-on experience.
Is it not possible to do it today? I am asking too much. Because just let me just tell Professor
Because,
Mohanty, he said
Siddharth,
that he will be unable to join. So I do not know if you can extend or we
That-
can just break and have
who
meet
said?
at 6 o'clock.
Who said, Siddharth?
Next lecture is by Professor Mohanty. So there is some urgent meeting there uh, in their lab, some visit of the director. So he said
We
that
could-
he will. Mhm.
We could do actually, but Siddharth, my plan was to actually ask each of them to go through the installation process and then run some programs. So maybe it will be tight today, I guess.
But if you can, means I'm wondering if you can do some part of that today, and then maybe if you can give some part of your lecture tomorrow to Professor Mohanty. Because we have time. Our next lecture is at 6.
Oh,
The special lecture is at 6. So if you can do that, but it all depends. If you are means ready for that, then only it is
no,
possible.
I'm ready, but I just wanted to go through it once, means in one
Okay,
go.
okay.
That would make more, I mean, you can also, because you are giving introduction and then explaining few things, and then you start with the hands-on experience. So I hope that would be better. Or if you want today to finish up to 6, then we can start after some time, maybe.
Not up to 6, maybe. So whatever time you use today, maybe that much time, if you can give from yours
Then I think I
to
would,
Professor Mohanty,
then I
maybe we
would
can.
go to next day. I think that would be better.
Okay.
Because it will have continuity in that sense.
Mhm.
Yeah. So I just have maybe some question for the audience, that do you think that you can do this homework today and send me? If you have some problem or any student, because I cannot see. I see few hands raised. Swapnesh.
Yes, hello.
Swapnesh, you raised your hand.
Actually, I
Right?
had a questions actually. That's
Okay,
why.
okay. Yeah, please.
Actually, those were the basic questions. But when you mentioned something about hit and miss, right? I mean, there is some selection criteria.
Right, right.
Yeah. So that what is the meaning? Why you use hit and miss? I mean, I saw just a condition of WI.
Okay.
So what is why we use hit and miss the terminology? Or is
Okay.
it just
I have not included that slide explicitly, but let me try to give you the basic idea. Why we call it hit and miss is that suppose in this particular example, which is shown here, you would calculate the area of square, right? By random number. And then you take a radius of circle, which is 1. Basically, x square plus y square is equal to 1, right?
Yeah.
So then you will try to get those points only which lie within this area. X square plus y square less than 1, right?
Yes, sir.
Otherwise, you would not add them here. So this is something called hit or miss.
Okay. So it depends on the problem in that sense.
Yeah, basically you compare with some standard thing. Suppose, let me try to go through some blank slide and maybe try to explain it here. So you have some distribution, let us say some kind of distribution F, and this is X. So what you do is you generate the random numbers. You generate the random numbers as per this distribution, right? And then in the second step, you generate the random numbers which lie between, let's say, this should be y, which lies between 0 to f max. This is f max, right? And you will compare this random number with the one which you generated, that is y compared to fx, like something fxi, you can say. If it is less than, if this one is less than this fxi, you would accept it, or you would not accept it.
Okay.
Otherwise, right?
So in case of event generators like this particle collisions, this fxi will be what? I mean,
say, can you repeat, please?
this fxi, which you mentioned. So it will be some kind of distribution in case of event generated in.
So those will be based on some letters. I mean, if you go through the theory, you know something like matrix elements cross-sections, right? So those things you want to calculate.
Okay. So fxi will be made up of those things.
Yeah.
Okay. So one more question. So you told us the comparison between the particle physics event generators, like the PYTHIA and heavy ion physics event generators. So you mentioned something about the background processes. So that one of the differentiating criteria. So you mentioned that in particle physics event generator, background processes are not much; they are easy to handle. But in heavy ion physics, they are not easily defined. So what kind of background processes are there, and how do you take care in heavy ion physics?
So because as we mentioned that heavy ion are nothing but you would say that there are many PP collisions, right? Not only that, you have interactions in PP collisions. In those collisions, you have interactions among the partons from different protons on, right? So what happens is, as a result, this becomes a very dense medium, and you would want to extract some signal from here. So it is like many things, and you are finding something of important to you, right?
Right.
So those kind of backgrounds are very cannot be easily defined in heavy ion collisions. But in PP collisions, you could simply extract your variable of interest, and there might not be much background in that.
Okay. And so how do we take care of those diagrams in this case then?
Basically, you would try to, for example, if I go through some observable, let's say you want to have some invariant mass of some particle. So what you do is you kind of use some background methods, like you mix the events which are similar to in your real data, but those are not correlated. So those will not show those effects which will be present in the real
Simulated.
data.
Mhm.
Yeah. So that way you can simulate the background, and then you can try to extract your signal.
Okay. Okay. Thank you, sir.
So, sir, are we also dealing with some smearing effect to make the simulation more realistic?
Yes. So this is what you do in your experiments, right? When you try to calculate your efficiency, acceptance, momentum resolution, so on. So there are some processes involved while the particle are going through the detector, and then you introduce those concepts there, and then you make it like I mean the backgrounds or whatever, you can do that. Yeah.
Okay, sir.
Did not get the answer from students. If they would do this exercise and homework today and send me. Any volunteer? Obviously, I will help you if you want to do that. So I would like, from all of them are conversed with the well versed with root, right? I think yes.
Yes, sir.
So it will not be difficult, and mostly I'm expecting students from 1 to 3 years. They should try to do this exercise and send me, so that we can say that you are trying to learn something. And the students who are little senior, I would expect them to do the second homework mostly, which is so that will be more beneficial to you, I think. Siddharth, anything else we would like to do? Because
No, if you are done, then probably we stop here today, and not today, but now. And because next lecture by Professor Gagan Mohanty is not going to happen today because he has some urgency there, so he could not do it today. And our special lecture is at 6 today. So now it is 4 o'clock. So maybe we meet at 6 o'clock. Maybe I would request to join a little ahead, maybe around 5:55 or 5 o'clock, so that 5:50 or 5:55, so that we can start the lecture at 6. Is it okay?